When I was first introduced to trigonometry, it was one of those subjects that I found especially confusing and unintuitive. The goal of this video is to take that introduction and expand it into something more general and hopefully more intuitive. But first, let's see what that introduction was. When trigonometry is first introduced, it is based on the right triangle. Essentially, we have three core ratios that we name sine, cosine, and tangent. So, the sine of a given angle theta is defined to be the length of the opposite side over the length of the hypotenuse. The cosine of theta is the length of the adjacent side over the length of the hypotenuse. And the tangent of theta is the length of the opposite side over the length of the adjacent side. The phrase SOHCAHTOA is very useful for memorizing these ratios. The letters stand for the certain sides involved in each ratio. This idea is a little weird though. We just gave seemingly arbitrary names to seemingly arbitrary ratios in this seemingly arbitrary setup. We are just memorizing these names and ratios without any deeper meaning. This setup is also very limited. Remember that the sum of the angles in a triangle equals 180 degrees. Since our right triangle already has a 90-degree angle, theta has to be between 0 and 90 degrees. This is very problematic. Suppose I want to find the sine of a right angle. I can't do it. The sine of an obtuse angle? Can't do it either. The sine of a reflex angle? Nope, not happening. So how do we solve this problem? So far, we have been thinking about sine, cosine, and tangent as ratios, a comparison between two things. We have to move away from this and start thinking about them as functions, something that takes in an input and spits out one output. And we want these functions to take in any input, not just ones between 0 and 90 degrees. Let's take a look at sine first. We just learned that the sine of theta is the length of the opposite side over the length of the hypotenuse. Now we want to think of sine as a function, so a good idea would be to set the length of the hypotenuse to 1. Now the sine of theta in this triangle would simply be the length of the opposite side. The input is theta and the output is the length of the opposite side. Sine looks more like a function now. Let's try to see what happens when we increase the value of theta. As theta increases, I have to rotate my hypotenuse because its length stays fixed at 1 for our setup. Now, I have to somehow draw a right triangle while preserving the length of the hypotenuse. To do this, my opposite side has to drop down. Notice how my opposite side, which is also the sine of theta, is bigger and how my adjacent side is smaller. Playing around with the idea that the opposite side is getting bigger and the adjacent side is getting smaller, how about let's draw the triangle associated with every value of theta between 0 and 90 degrees, incrementing by 5. As the value of theta increases, I simply rotate my hypotenuse theta degrees and drop down the opposite side to create my triangle. In addition to looking cool, doing this with all of these values of theta, a very interesting pattern emerges. Look at how nicely a circle with a radius of 1 fits in. This should make sense. Let's quickly review the definition of a circle. A circle is essentially the collection of points that are a certain distance away from a certain point. That distance is the radius, and that point is the center. There will be infinitely many points, but each point will have a certain rotated hypotenuse associated with it. Therefore, each point will have a certain value of theta associated with it. and the sine of theta is going to be the distance from the point on the circle to the bottom of the triangle. Make sure that's clear. Each point is associated with a hypotenuse rotated theta degrees, and the sine of theta is the distance between the bottom of the triangle and the point. Now we can rephrase our definition. As I walk theta degrees along this circle of radius 1, the sine of theta just becomes the length of the green segment. Now we can introduce the final formal definition. I'm going to draw the coordinate plane in a circle of radius 1, which is called the unit circle. I will place its center at the origin. Now, as I walk theta degrees along this circle, the sine of theta is the distance from the x-axis. And I will not limit myself between 0 and 90 degrees. I will keep going. I will break out of the triangle entirely. If I go below the x-axis, the value of sine simply becomes negative. I can also find the sine of negative values by walking in the opposite direction. This is the full final definition of sine. We expanded it in a logical way, and this function can spit out outputs for any input. But the question still remains, why do we have a function like this? Why is it defined in this weirdly specific way? Why do we even need a function like this? Well, if we graph this function, with the input being the value of theta and the output being the length of the red segment, it has a wave-like pattern where we essentially cycle through the same set of numbers. In many math and physics problems, we need to describe wave-like patterns. This function describes the natural world around us. You may also be wondering about the extended definitions of cosine and tangent. I will leave that as homework. Try to go through the same line of reasoning as we did here.